All right. So today and tomorrow, I want to talk about statistics for partitions of n and how they're distributed as n tends to infinity. So you can pick a statistic for partitions of n, like the largest part, and you can ask, okay, how is that distributed among partitions of n? But we want to look at what happens as n tends to infinity. Is there a limiting distribution of these statistics as n tends to infinity? Okay. So yeah, we can ask, how are certain statistics distributed on partitions of n as n tends to infinity? Okay. And I'll give you an example of this if you're, not so familiar with probability distributions and haven't thought about that a while since undergrad. I'll remind you of some of this with some examples. But let me start off with a simple question. Okay. So for example, what's the probability that a partition of n contains a 1? What's the probability that a partition of n contains a 1? What do you think? Mm-hmm. Yeah? Nick? 1? Well, okay, you mean as n tends to infinity, it should be 1. Yeah, so as n tends to infinity, Nick's claim is that 100% of partitions of n should contain 1s as n tends to infinity, which makes intuitive sense. But can we prove that?
You gave us the big guy in the S and Ks.
Yeah, but how are we getting at partitions that contain 1s? Yeah, I mean, no, this is the right idea. So, okay. Yeah, so we want to count the number of partitions of n that contain a 1. So maybe let me just say 1 is n lambda divided by p of n. And we want to look at what happens as n tends to infinity. But what's the numerator? You gotta pull out your combinatorial brains a little bit here. The numerator is something nice. Anybody? So if I have a partition with a 1, what can I say about the rest of it?
It's a partition of n minus 1.
Partition of n minus 1. Right. And given any partition of n minus 1, I can always stick a 1 in there. Right? So there's a bijection between these two things. So the numerator is p of n minus 1. And these are asymptotic, so it goes to 1. Okay. Now today I'm going to edit my questions a lot, which you should never do if you're teaching, but it's okay here. Okay. So we get a 1 here. So what if I change the question and maybe make this into a 2? So what's the probability that a partition contains 2? I put a 2 in here. All right, now how does this change? P of n minus 2, right? Because given any partition of n minus 2, I can always stick a 2 in there. And then we get a partition of n that contains a 2. So this also tends to 1, right? Is there anything special about 1 and 2? No, right. I can change the 2 into any part k, and this is true for any fixed number k. Now, fixed, when we're talking about asymptotics, this means that, well, something's tending to infinity, n's tending to infinity, but k isn't. K is just fixed. K is 100, 1,000, a million, anything, but it's not tending to infinity. So, and we could even go further. We could say, what's the probability that a partition of n contains 10 ones, 3 twos, 4 fives, etc. And we just adjust this, we subtract that off, but it's going to tend to 1, right? So I think I've convinced half the room of that. So what does this tell us? It tells us to get interesting distributions of these sorts of things, we're going to have to let these parameters depend on n. Okay. So before I scare you with letting things depend on n, I just want to motivate that a little bit. So basically, to get interesting distributions, whatever that means, we will want to let these parameters depend on n in some way. So we will let the parameters depend on n. Okay. All right. Let's take another example. So I'm going to let x1 of lambda be the number of ones in lambda. In the partition lambda. Okay. So most people would use like m sub 1 for the multiplicity of 1, but we're going to get into the probability, and so this is the notation that I'll use, x sub 1. So for example, x1 of, say, 5 plus 3 plus 1 plus 1, what would that be? 2, good. Yeah, so there's 2 ones in that partition. All right, and let me make a table for n equals 10 and show you how this guy is distributed. So I'll take n equals 10, and for various k's, we'll look at the number of partitions of 10 with k1s, and we will also look at the number of partitions of 10 with, at most, k1s. Okay. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So, 15, 8, 7, 4, 4, 2, 2, 1, 1, 0, 1, and 12, 20, 27, 31, 35, 37, 39, 40, 41, 41, 42. Okay.
How is the first column together?
The first column is your k.
No. Corresponding to k equals 0. What's different for that?
So this is the number of partitions of 10 with 0 ones.
And downstairs?
And downstairs is this inequality. So number of partitions of, oh, you're right, they should be the same, shouldn't they? Uh-oh. Maybe, Will? Maybe this is supposed to be 12. I don't know. 12? Yeah. I think that should be 12, probably. Oh, y'all can check me. Yeah, thanks. So if we divide these by P of n, this in probability is known as the probability density function, or the PDF for short. I won't use this, this terminology, but just to remind you, so it's the probability density function. If you divide by 1 over P of 10, which is 1 over 42, and then this guy is the cumulative distribution function, the CDF. Cumulative distribution function. Okay. And I'm going to let capital P sub n be the uniform probability measure on partitions of n. So this is the uniform measure on the set of partitions of n. That's just a complicated way of saying that a partition of n gets probability 1 over P of n. I just want this notation because now I can talk about, you know, P of n of x1 equals something. Okay, and if we graph, 0, 10, 42. So if we graph this guy, this is the cumulative distribution function. You know, so this is the partitions of 10, and I guess I should say 10 because I'm doing partitions of 10. So it's the number of partitions of 10 with at most k ones divided by P of n. This is the cumulative distribution function, and if we graph the data that we have over there, actually this should tend to 1, not 42, then, okay, well, we get some step function sort of a thing. That looks like this. So we want to work out how x1 is distributed under P of n as n tends to infinity. So let's look at P, well, let's see, should I do 10 or? Yeah, okay, so I'll do this in general, and let's write down an expression for this guy and try and estimate him asymptotically. So I'm looking at the probability that a partition of n contains at most m ones. Okay, so first of all, that's the sum of the probabilities that x1 equals k for k from 0 to m. And what I want to do with each one of these guys is represented as a coefficient in a generating function. Can anybody tell me what it is? Okay, so, all right, this guy, this is 1 over P of n. And then what I'm going to put here is the number of partitions of n with k ones. So somebody tell me what that would be. Number of partitions of n with exactly k ones. Can we represent that as a coefficient in a generating function? So I've got k ones, and the rest of the parts I get to choose. Yep, come on.
So it's the coefficient of q to the n minus k in 1 minus q divided by the q to infinity. It's just p then minus k?
Yeah, yeah.
M, sorry, yes.
Yeah, so let me write that this way. It'll be the coefficient of n where I've got k ones, and then the rest of the parts I get to choose as I like. So j from 2 to infinity, actually. Okay, right? So I've got exactly k ones, which is why that factor is missing from the product. And then the rest of the parts I get to choose. So it's the coefficient of n there. And let's see, so you can mess with this product a little bit. You can add up the geometric series here. And so what you will get is 1 minus q to the k plus 1 over 1 minus q times this guy. And you can combine those. So we get that expression. Oh, that should be m, thank you. I was using k in my notes and then changed it to m. So yeah, that's what we get. All right, and I want to finish this calculation in two different ways. Well, one more precise way and then one more heuristic way, which is going to be more enlightening in the end. So the first way we will finish this is to see that if you separate this guy here, well, what's the coefficient of q to the n in 1 over q infinity? Anybody? So if I take the first summand here over this, what's the coefficient of q to the n? It's p of n. And then here, it'll be p of n minus m minus 1. So on the one hand, this is p of n minus p of n minus m minus 1. Or if I divide, we get this. And now we plug in the asymptotic formula for these guys. And I will do some simplification. But if we plug in the asymptotic formula, we wind up with, okay, this thing divided by the same thing, exponential of pi root 2n over 3. And then here in the numerator, we have the same thing. And the next term is minus pi k over root 6n. And then there's some error. K squared over n 3/2. Okay, so all I'm doing is plugging into the asymptotic formula. And in the numerator, I've just simplified. Oh, again, I used k. Sorry, should be m. Thank you. And yeah, so all I've done is simplify the square root when you plug in the m there. And what happens is that, well, this and this and this cancel. But if we want to get a meaningful expression in this guy, if we want to get something that tends to a limit as n tends to infinity, we will choose m depending on n in a certain way. So we'll set m, and I'll choose it in a way that clears these constants. So I'll make it root 6n over pi times u, for u now a positive real number, or non-negative real number. Okay, so this is what I meant when I said over here that to get interesting distributions, we're going to want to let parameters depend on n. So in order to get a meaningful distribution for this, we need to let the m there depend on n in this way. Okay, and if I do that, then I just get 1 minus e to the minus u. That's what I end up with. So there we go. We have our first theorem due to Fristet in 93. So he proved that the limiting probability of x1, and now I'm going to use that substitution in n, in m. Root 6n pi u. The limit as n tends to infinity is 1 minus e to the minus u. And sometimes we want to rewrite this by putting this over here. So let me just go ahead and do that. So pi over root 6n. So now it looks a little bit nicer. So in the literature, this is known as an exponential distribution. And yeah, so you get an exponential distribution when you rescale the number of ones by this constant here, depending on root n. So for example, let's see, where's my example? Put it somewhere. Yeah, here we go. So for example, if we want to look at the number of partitions of n that contain at most 2 root n ones, then this guy's n tends to infinity is approximately 92%. So the interpretation is, 92% of partitions of n contain at most 2 root n ones as n tends to infinity. Yeah. And now I'm going to do what I did over here. We're going to change 1 to something else and see what happens. So instead of doing the number of ones, let me pick a different number. Well, we'll do 2. We'll start with 2. So now let's do the number of 2's less than m, and let's see what changes. So I'm going to have the probability that there are at most m 2's. That's equal to the sum of the probabilities that there are k 2's. K from 0 to m. All right, and now what changes in this line? Somebody let me know. What's going to change in this next line if I'm looking at the number of partitions of n with exactly k 2's?
You want 2k?
So yeah, first of all, we want 2k because, all right, I'm saying I have k 2's, so I have a contribution of 2k, and then the product here, I need to have everything except the second factor there, right? So I want to start at 1, and I want to get rid of the factor where j equals 2. So let's just go ahead and do that this way. Okay, everybody okay with that? All right, and then, so let's just correct this. So then I have 2m plus 2 in the next line, 2m plus 2. Right, and this should be 1 minus q squared. So this and this cancel. We get this guy. And now I'm going to have p of n minus 2m minus 2 here. 2m minus 2. All right. And then here, what's going to happen is that I'm going to get actually a 2m here. So I get an extra factor of 2 there. And so now it's best to substitute m like that with a 2. So we remove the factor of 2. And then we get the same thing, 1 minus e to the minus u. So now it's going to look like this. So the probability that there are at most this number of 2's when you rescale tends to an exponential distribution. And there's nothing special about 2. You can replace 2 with any fixed number and get a similar result. So now I want to adjust this calculation one more time. And I want to count 1's and 2's simultaneously. Yes, please.
Why do we have 2 in the denominator but not in the numerator? In the last formula you wrote.
Here?
No, I believe that, but the next one.
Here.
Yes.
Because that's our substitution for m. So it would be x2 less than or equal to m. And m we're replacing with this.
Yes, but 2 is together.
Oh.
But not anymore.
Yes, you're right. I see. So it should be up here.
Yes.
Yes, I think that is probably a mistake I made in my notes. Okay. Yeah, maybe I'll have to double check the literature and see if that's wrong tomorrow. But yeah, that seems to be right. Yeah, sorry about that. So the factor of 2, it looks like, should be in the numerator. Yeah. Okay. So yeah, now let's try and count 1's and 2's. So let's look at the probability that m1 1's and you have at most m2 2's. So I just follow my calculation over there. So now we sum from K1 from 0 to M1. K2 from 0 to M2. And we're going to say that our partition contains K1 1s and K2 2s. So Q to the K1 times 1 plus K2 times 2. And then we want to generate all the parts that aren't 1s or 2s. So I want the product without the factors 1 minus Q and 1 minus Q squared. I want to get rid of those because I've chosen how many 1s and 2s I'm going to have, and the rest of the factors are here. So, summing the geometric series once again, we will end up with 1 minus Q to the M1 plus 1 times 1 minus Q to the M2, 2M2 plus 2 over this, coefficients of Q to the N. And then, if I want to finish the proof in the same way that I did over there, well, I'm going to multiply this out, right? And I have 4 terms. I have 1, Q to the M1 plus 1, Q to the 2M2 plus 2, and then plus Q to the 2M plus 2M2 plus M1 plus 3. And then I will get 1 over P of N minus P of N minus M1 minus 1, P of N minus 2M2 minus 2, minus P of N minus M1 minus 2M2 minus 3, right? Close parentheses. Sorry?
That last one is plus.
Yes, thank you. Okay. And once again, if we do the asymptotics in the same way that we did here, you can make the same substitutions. So once again, we'll set M1 as, what is it, root 6n over pi u1, and M2 as root 6n over 2 pi u2. Is that what we did? Yeah. And if you do the simplifications, you get the following. That the probability that pi x1 over 6n is less than u1, and the probability that 2 pi x2 over root 6n is less than u2 is asymptotic to the products of those two exponentials we got in the original case. And this is due to first step again.
I have a question.
Yeah.
Is there a specific reason for the choice that we want the numbers 2, 3 Not with U2, but with the statistics x sub 2, x sub 3, rather than writing 1 minus e to minus 2 times U2 and stuff like that. What's the reason for that?
You could restate it that way if you wanted to, I suppose.
Yes, but is there a reason for the choice?
Yeah, so the reason is that these are both the same, and that's just kind of nicer. So these are both, this is a product of exponential distributions. So and yeah, this leads into the next thing I was going to say. So we can learn a lot from this calculation here. So in the limit, we get the product of these two distributions. And in probability, that happens when the random variables are independent. So what this is telling us is that in the limit, the number of 1s and the number of 2s are independent. So let's write those observations down. And actually, before I do that, let me just go ahead and tell you that you can do this with any number of these xk's. So Frista, proved the same thing with with the x1, x2, x3, etc., up to any xk. So if you look at the probability that, say, pi xj, well, I guess I need j up here. So j pi xj over root 6n is less than uj for j from 1 to k. Then you get the products of all of these exponentials. And in fact, you can even let k depend on n. So side note, so we can even let k in this theorem depend on n as long as it's smaller than n to the 4th, I believe. So I want to keep, let's see. All right. Let me swap these so that I can point at that. So let's make some observations. So what this theorem tells us is that these xj's, if we rescale, behave independently. We get the products of these exponentials. And that's good in terms of probability. So the x1 up to xk are, or let's say, become independent in the limit as n tends to infinity. That's what this theorem is saying. On the other hand, they're not independent under the uniform probability measure on partitions of n. So, but we know that these guys are not independent under P sub n. And that we can see actually from this calculation, because swap this again. So this guy right here, this is the exact probability of what I was trying to get, of this guy. And this guy is not equal to the product of these two probabilities. Let's see. If you take this times this, right? I forget what this was exactly. This was something like 1 minus p of n minus m1 minus 1 over p of n. And this guy was 1 minus p of n minus 2 m2 minus 2 over p of n. That times that is not that, right? So these are not independent under p of n, but they become independent in the limit. And independence is good, as we will see. Any questions up to this point? Okay. Let me check the time real quick. Okay. So some more observations. First of all, the sequence of xk's determines a partition. Right? So if I tell you the number of ones, the number of twos, the number of threes, etc., then there's a unique partition with that number of twos, number of ones. Right? So for example, I don't know, if I say that x1, x2, x3, x4, x5, if this equals, I don't know, 1, 2, 0, 3, 1, 0, 0, 0, etc., then that corresponds to the partition. Well, y'all tell me, what partition would that be? Yeah, come on.
5 plus 3 fours, 2 twos, and 1.
Yes. Right? So we have 1, 5, 3 fours, 2 twos, and 1, 1. So the xk's determine the partition completely. So that means that any statistic that we can describe about partitions, we can describe in terms of the xk's. Right? So you can describe the largest part. You can describe the rank of a partition, if you know what that is. You can describe the size of the Durfee square. You can describe all kinds of things. And leave it as a homework assignment to you to think about how to describe some of these statistics I've named. But basically, what I want to get to talking about is the work of Bert Fristet. So I've mentioned a couple of his results from his 93 paper in the Transactions of Mathematics on how to do statistics for partitions. And what he invented for partitions was a certain way of using these observations here. That the xk's determine the partition, so they determine any statistic, and they become independent as n tends to infinity. So he introduced a certain probability measure on partitions that takes advantage of this stuff. So that's where we're going to go. Actually, before I do that, let me give an example of a statistic. Okay, so for example, all right, I'm going to use his notation, which is maybe a little confusing, but I want to stay consistent with him. So I'll say that n, capital N, of lambda will be the size. And so sometimes people and partitions use like absolute value of lambda for the size. All right, so what's capital N in terms of the xk's? I claim that we can write that in terms of the xk's. What would that be? Yeah. The sum of what?
K times h.
Yes, very good. So we add up k times the number of times k appears. Right? This is k times the number of k's in lambda. And for a partition, well, it looks like an infinite series, but a bunch of those are 0. Okay. Great. Yeah, and so for example, in this example I have up here, well, maybe I don't want to add them on the board, but m of that partition would be the size, right? Okay. So I will now introduce the Boltzmann model. For partitions. So this is going to be a probability measure that is, let me just roughly say, better than the uniform probability measure, but in some sense the same, in some sense equivalent. So what you do is you pick a real number between 0 and 1. So this week, Q has been mostly a formal variable in other people's talks, but for me, this week Q is a number, a real number. And so here, you just got to keep in mind that this is some fixed real number in between 0 and 1. All right, so then we will define for any partition, so this will be the set of partitions, all partitions, not just partitions of n. We'll define this probability measure Q sub Q of lambda as Q to the size times QQ infinity. Or if you want to think of this as the generating function, you can think of it as Q to the size divided by capital P of Q, the generating function for partitions. So maybe this is the better way of thinking of it. So I know Q is a kind of weird notation for probability measure, but I think he uses Q to not confuse it with the capital P, which is the uniform probability measure, okay? So we have two probability measures on partitions. We have the uniform measures, capital P, N, and then we have the Boltzmann model, okay? And what I want to do before showing, so I think tomorrow I'll show you some applications of this guy, what you can do with it. For example, it was requested to see an algorithm for generating partitions. So you can use this to generate partitions in a really fast way. So maybe I'll do that tomorrow. And maybe we'll do some other cool stuff with it tomorrow. But what I want to do today is just prove some simple properties of this guy, the Boltzmann model. And so also the terminology Boltzmann model is not what Fristet used. This came later when people figured out how to do these for combinatorial structures in general. But okay, so proposition, basic properties of the Boltzmann model. So first of all, it's a probability measure. Second, it's uniform on partitions of N. So in fancy probability language, this says that the uniform measure equals QQ conditioned on the size being N. And finally, the xk's are independent under this probability measure. And I can tell you their distribution as well. So the probability under the Boltzmann model that you have jk's. So there are jk's in the partition. This is a very simple expression. It's 1 minus q to the k times q to the kj. So this is a geometric, if you know the terminology, this is a geometric random variable. So geometric distribution. Okay. Do we have any questions about anything? Okay. So we have all these nice properties about the Boltzmann model. And they're actually pretty straightforward to verify here. So first of all, why is it a probability measure? In other words, I need to show that if I add up all the probabilities, I get 1. That's what I mean by that. So I want to look at adding up all the probabilities, and I want to get 1. Now, I'll just use the second formulation here of the Boltzmann model. So we just plug that in. You get q to the lambda over p of q. Factor the p of q out, and then we have the generating function. So it's just p of q over p of q, which is 1. So it's a probability measure by definition. Okay. So the uniformity is actually also really easy to see, because if I take 2 partitions of the same size, then I get the same thing, right? So it's uniform. For any partition of n, we get that the Boltzmann model equals q to the n over p of q. And just the fact that this is the same for any partition of n means it has to be uniform on partitions of n. Why am I using red? If you want to do this a bit more explicitly in terms of probability, I'll go ahead and write that out too. But in fact, that's all you have to say. But if we want to be more explicit, yeah. So we want to check this condition here, that QQ of lambda, conditioned on the size being n,